kind of after-the-fact approaches to LangSec using machine learning with somewhat of a grounding in grammatical inference. So just a quick outline. I'm going to walk through the theory of kind of why we needed to do what we have attempted, starting with grammatical inference, tying it into LangSec. We'll cover the paper. The general idea is to use machine learning to bypass the hardness results that we'll discuss. I'll discuss the experiment results and kind of our upcoming future work and close it out. So to start from kind of first principles in grammatical inference, we can think of grammars as a tuple where we consider a set of non-terminal characters, a set of terminal characters, which is disjoint from the non-terminals. The terminal characters can be thought of as the alphabet. That's if you see an actual word, the terminal characters are what you're looking at. A set of production rules that gets us from the non-terminals to the clean star set of terminals and non. And a set of starting characters, which will be a subset of the non-terminals. In general, grammars will generate language, which here we're just going to use that as the set of all words that are in all possible enumerations of the alphabet, such that you can reach those words by using the production rules and starting at one of the starting characters. So when we define these languages, it can tie into the idea of the Chomsky hierarchy, and this gets into the complexity. And the 4 levels of complexity, the 2 that we're most interested in, both from a LangSec standpoint, but also just in general, are going to be regular and context-free, where context-free we can consider either deterministic or non-deterministic grammars within it. So basically, we're going to deal with these 2, and we're interested in pursuing context-free just because that's what we often see. The key questions that we're going to take away from the grammatical inference side is, given a particular grammar, can we determine what its produced language is in its entirety? If we have 2 grammars or 2 languages, can we determine if they're equivalent in some way? And if we're given samples of a language, so positive string examples, can we learn a grammar from that? And as it turns out, in the realm of theoretical grammatical inference, the answer is mostly no. Unless if you're anywhere above regular, you basically cannot create a general learner. And even in the case of regular, you need something like a complete expression, which means that you have both a list of words that are in the language and also a list of words that are not in the language. Even if we relax to simple probabilistic identification, such as Valiant's idea of probably approximately correct, still learning is generally considered extremely difficult, if not NP hard or NP complete entirely. There's a few examples of languages that are learnable, but they're kind of very specifically created to be such. I'm going to briefly talk about 2 of them, particularly Anglin's pattern languages and Clark's non-terminally separated. These are just kind of like examples to paint a picture of what we're trying to deal with. So from a pattern language example, that top part's the definition. It's heavily into math, so if you don't want to read it, don't worry too much about it. Basically, an example of it is if we're given a simple alphabet, say 0 and 1, so a binary, we can construct a pattern. Here, x1, x2, x3 are variable stand-ins for the alphabet. Then we can consider a set of words where we've made substitutions for those variables, and that would be a subset within the language generated by that pattern. Again, the issue with this is that it's a very restrictive language. It's pretty unlikely that you'll, in practice, come across something that has a nice pattern breakdown like that. And even if you do, determining equivalence between these 2 languages is still NP hard. So it doesn't necessarily spare you if you're trying to identify which language you're looking at. From the NTS language, so this is a context-free grammar example that is actually shown to be exactly learnable. There's an in-depth discussion by Clark in a paper he wrote when he won the Omphalos competition for building grammars from positive strings. An example of the grammar his algorithm produces is on the bottom right there. It's actually truncated. It's about 3 times as long as that. And the strings that were given were pretty short, and the characters that were present in any given language were, not a full alphabet, so you're talking about 10 to 14 characters possible. And despite that the grammar is enormously complicated. So the takeaway from this is that we can get exact results for very particular subsets of grammars, but in his example, his algorithm is quite slow, impractically so, and it may not converge reasonably, which is to say that it may converge at some point theoretically, but it could be after the heat death of the universe or something like that, so we simply can't wait around for that algorithm, even if it can indeed produce results. So from a LangSec standpoint, what this means to us is that learning grammars is hard. So we cannot determine if a parser's grammar is equivalent to another. So even if we know a grammar that is, say, compromised, or even if we know a grammar that is valid for all possible, we can't necessarily tell if the one we're looking at is the same. It's generally not possible to enumerate all safe or bad strings for a parser, especially if it's not of a finite language. And you cannot generically learn all parsers using a single method. So even though Clark's and Anglin's examples of languages that are directly learnable exist, those same methods don't, say, learn any given regular grammar or any given context-free grammar. They only learn those very specific subsets. But we still want to try to get with the idea that parsers should be restricted to the low level in the Chomsky hierarchy in order to maintain security. But that's kind of difficult when a lot of people either want it to continue using what's easiest or don't want to try to rewrite what they consider not broken. So in order to get around that, we're going to relax the idea of exact learning and use the fact that we know that computers are discrete and computational. There must be some underlying structure, even if it's not necessarily clear to us, and even if it's not necessarily a secure structure. And rather than exactly trying to learn that grammar, we're going to try to do, say, close recognition. We're going to relax our assumptions heavily and just try to be good enough so that we can kind of apply at least some level of security, even in a situation where the people who are working with your parser aren't willing to change to more secure systems. To do this, we're going to use machine learning. Basically going to build and train feature vectors from language examples. This will be from positive example. And the key differences between exact and machine learning is basically you can think of exact learning of a language as building sentences from parts using rules if we consider it in the context of natural language. Whereas with machine learning, we're not going to necessarily be able to construct the rule set itself, but we're going to be able to recognize whether or not a language is actually present there. And we're going to do it only by knowing what the letters are that go into it. So we're not going to need to know any other specifics besides seeing the letters. And some positive examples. The network we use is a multi-layered LSTM. It's a long short-term memory. It's by a paper from Hochschweider and Schmidhuber. So you can take a look at that if you're interested. Basically, our input is a one-hot feature vector input. It has one-hot encoding for the various characters that can appear in the alphabet. In our case, it was 102, just because of what the training set is, which we'll get into. That goes into an embedding layer, which kind of abstracts the feature vector into some kind of weight matrix, and then goes through a series of LSTMs, which we'll discuss in a moment, before finally coming to some normalized output vector. Usually, that could be either another one-hot feature vector, or it could be a classification label. So for the LSTM, just a real quick, real short summary of it. That's kind of a picture there of an unwrapped LSTM. The idea, it's a type of recurrent neural network. It's feed-forward, so you give it an input, it'll feed forward into a series of weight matrices, which will then eventually produce some output. It also simultaneously feeds back into the same layer. You can think of this as having some kind of idea of a stateful memory between each of the iterations in the learning period. And LSTM in particular has this idea of a stateful memory that is maintained and edited kind of sparingly. So edit limited doesn't mean that it's not allowed to be edited. It's just kind of, there's some restriction to how much the weights can be edited at any given moment. The nice thing about LSTM is that they're able to learn over what are called long distances. So if we're discussing something like trying to learn a language, that's what we're interested in because we'd like to have some kind of dependency across the characters. So with that as our network idea, the training data we're using is labeled URI data from Apache server logs. We stripped out all of the stuff like IPs and any kind of headers or anything like that. It's literally just the URI plus the response code from the server given that URI. It is possible because of this you could have multiple labels, especially once we start grouping. So that we'll get into why that's not necessarily great, but we're already relaxing assumptions anyways. As far as the network is concerned, a URI is completely unknown to it. It doesn't know what the structure is. It knows nothing about the RFCs or any kind of convenient constructions. The only thing it knows is that a URI is constructed of a series of letters, and that we're going to give it examples of what a URI is or what it shouldn't be. Our goal here is validation. So we would like to recognize only valid URIs so that if someone tries to send an invalid URI or attach something to it that shouldn't be in a URI, it rejects it. But otherwise, we also don't want to reject perfectly reasonable URIs. So here's the results. The first one is the table. So here we're talking about the Bayes accuracy. Whenever you're dealing with a labeled data set and any kind of prediction, the Bayes error rate's the absolute best you can get, just especially if there's overlap in the labels. This basically represents the percentage given that you randomly draw and get it correct despite there being an overlap. So because there's multiple labels possible, it's impossible, even if your identifier is perfect, to actually get 100% accuracy, so Bayes is the best we get. Ungrouped versus grouped is, again, this idea of whether or not, ungrouped means that we allow for any possible server response code, so labeling it 501, 502, or whatever. Grouped is saying handled, not handled, or server error. In general, there weren't really many server errors, but they are technically possible in the group data. Table 2 gives a breakdown of a particular, it gives a true positive, true negative, and all that good stuff for a very particular subset of the table 1. And so the takeaway from these two tables is that for recognizing valid URIs, we can do exceedingly well. When we try to look at is this a valid URI after a long extended learning period, with 99% accuracy, it'll return yes, this is a valid URI. And on even some of the invalid URIs, it will in fact return that no, this is an invalid URI. Downside, as I'll get into, is if you notice the false positive rate is a little bit high, but there's probably ways to reduce that. So again, the takeaway is that practical learning is possible. So even though URIs can, in theory, be a CFG, and even though we're dealing with a not well enumerated grammar, and even though we don't know what any of the structure is, we can still get recognition rate well above 99%. False positive rate at the time remains high. We also did generation of URIs. That's also theoretically possible since we did character by character learning. So we are also able to generate what would be considered reasonable looking URIs. Whether or not they're actually valid on the server is a different question. So indeed, we can train a network to recognize URIs. We need no prior knowledge. The downsides are that false positive rate is high. Training is very time consuming. And if we want good practical use, we'll probably need faster identification. So this segues into future work, which is it's very possible that we can use some kind of entropy-based rule set based on any given step in the character creation. And from that, we might be able to, say, make a finite state automata or something similar. And from that, we can construct a rule set that'll act much quicker than the network itself. The additional issue whenever you're doing training with neural networks is they might be vulnerable to malicious training. If someone gets, for instance, puts in data into your good set that's actually invalid. So we're doing work on determining the robustness of training in neural networks, assuming malicious traffic's included. So that's kind of where we're heading. So kind of bring the whole talk together. Theory is often hard, usually very hard, NP hard or NP complete when you're talking about learning grammars from positive example. There's no clear exact learning results. However, we have good experimental results. So it seems like it may very well be possible to kind of just throw enough computational power and give it valid URIs, and we can get something that actually does recognize URIs going forward. And it's not perfect, and certainly is not going to be a long-term solution, especially in the realm of LangSec, but it may be good enough to convince people who are otherwise not willing to adopt more perfect parsers to kind of, here's something that you can tack on in the meantime to try to help secure it a little bit more. But with that.